Let's actually go ahead and start it up on the boards. So we've got, I would argue, 3 tables worth of people, ish. I think that works. You've got compound A, B, and C. Within your group, write out this information and then come up with any piece of information that you think belongs in any one of those boxes. So try to process through and figure out what things belong in those boxes, if anything. Okay? And if you can't figure out anything, that's also okay. I still want you guys to talk through it, draw out those structures, and start to come up with some guesses and approximations of what each of those reagents could be doing, which then means what would be in that previous box. Okay? This is exceptionally challenging because you haven't seen the VIDIG. So what I'm trying to get you to do is apply the knowledge that you already have in a very limited sense to try and figure out what structures are there. Kind of make sense? Yeah. Okay. So, and it sounds like we've got a couple interesting questions popping up around this reaction, and we can definitely talk through some of those. Okay? But before we go into some of the details on this, I want to point out that when you look at any question, it's not just a solve this. You're given bits and pieces of information. Use those bits and pieces of information to help you whittle away at the larger problem. Okay? I'm not saying make this. Okay? That's not the question. Okay? What the question is make that from that reagent. Okay? So what we would want to go through and do is the same stuff that we've been doing in every other scenario. Let's look for where we see reactive things. So in talking through with several of the groups, they say, well, we see charges. Okay, we've got a positive and we have a negative charge. I had one group that say, shouldn't there be a lone pair there? Yeah, it's a negative. We should see a lone pair there. Okay? Why did they not show the lone pair? Because when we get to second semester, we decide as organic chemists that our students know enough about the octet rule and electrons that we no longer have to be extra specific in showing those lone pairs. Is that a good decision? No, that's a horrible decision. And I would argue that regardless of where you're at, you should be showing those lone pairs and not forgetting them. Because just like with the hydrogens, the instant you stop writing them out will be the instant you forget that they're there and you won't use it. Right? So if we look at that as a reagent, okay, or not a reagent, it's an end, what do we see as potentially reactive? Where are you like, ooh, that looks kind of crazy. I shouldn't have that. Okay? Most people are going to jump on that negative carbon. Ooh, negative carbon, that's not great. Okay? Which likely means that negative carbon was produced in that chemical reaction. That was the product of that chemical reaction. Which means if I backtrack, right, I could redraw all of those other pieces because those weren't relevant to the question. And I could just say, well, all of this stuff had to be there. That was there already, and somehow or another, I was able to change the properties of that carbon to make it negative. So something had to happen, some kind of chemical reaction. Okay? Defining what that chemical reaction is should be based off the reagent we react it with. Okay? So instead of looking at the product, we could have looked at the reagent. And I saw lots of people being like, oh, well, that reagent is right here. There's my carbons. Okay? Well, maybe. Okay? And I would argue the mistake that you're making there is that you opted to just look at the formula and not actually write it out. Because if we write that out, we have a CH3, so a carbon, bonded to a CH2, bonded to a CH2, bonded to a CH2, bonded to a lithium. That would be 4 carbons. I don't have a 4-carbon chain in my product. Okay? If I did, this problem becomes much more challenging. Okay? Which means that carbon, that structure there, didn't get added to, quote unquote, the structure. Okay? It had to have done something else. Okay, well, what things are accessible to me within that reagent? Okay, when we looked at our final product, oh, it's charged. Well, when you look at this lithium compound, I don't see any charge. But what should you see? I can accept a metal. Okay? Not only do I have a metal, but what is that metal connected to? You didn't tell me lithium, so don't tell me carbon. What is the metal connected to? A nonmetal. What kind of bond is that? That's an ionic bond. Since it's an ionic bond, it's better to represent the reactivity of that structure as a lone pair on the carbon and a positive on the lithium. What's the reactivity of those two structures? Which one am I most concerned about? The negative carbon. What could that negative carbon act as? Nucleophile. If it acts as a nucleophile, it's sharing electrons with something other than hydrogen in my left structure, which means I've made now a chemical connection between the left structure, okay, this red one here, and my blue one, which means in the product, what should I see? A 4-carbon chain. Do I see a 4-carbon chain? No, which means it's not a nucleophile. Well, what other chemistry does a negative charge have access to? Base. Which means this structure had to act as
an acid.
Okay. And I know extra specifically what atom had to act as an acid. And a couple different answers we could run with that. Okay. Let's take a step beyond hydrogen. Yes, the hydrogen had to act as the acid. But what atom was the hydrogen connected to?
Carbon that's connected to a phosphorus.
Okay, we could say the carbon connected to the phosphorus. We could also say the one that was circled in blue, right?
Yeah.
Okay. It had to be that hydrogen. Why?
Phosphorus would it be an inductive effect on?
Okay, so we can run all sorts of nasty questions with this on answering the why. So, well, phosphorus is electron withdrawing. Phosphorus is lower in electronegativity than nitrogen. If it was a nitrogen, that hydrogen's not acidic. Okay. The why here is less what is the general theory of how this could happen. Because it isn't that. I know what the answer is. I know I had to remove a hydrogen from that carbon because in the product, that carbon is negatively charged. I don't have to get grand with my whys. Okay. We'll come back to that in a second with that why it is because it's weird. Okay. Because I think there's a really solid, strong argument that that is not acidic. Okay? So you now have another starting structure. I don't remember what the next reagent was, PPH3. So we go back another step and say, well, it's adding PPH3 as the reagent. Well, now what had to happen? What was the precursor to that? I could again try to look for chemistries, but again, we're looking for whatever patterns we can see. Do you see PPH3 in that product?
Yes.
Yeah. Which means that bond was likely the bond that was made, which means I need to have that split off. The PPH3 is somehow connecting to that green structure, and it's connecting to that green structure at that blue circle. How is it connecting? Should my green structure be negative or positive? Should that carbon be negative or positive? Okay. How do I know? I should know because instead of looking at the formula for the reagent, I look at the Lewis structure. And when I look at the Lewis structure for that reagent, hopefully I've done enough Lewis structure practice to recognize that phosphorus is in the same column as nitrogen, which means 3 phosphoruses around it and a lone pair on the nitrogen, or on the phosphorus. That phosphorus having a pair of electrons could act as a nucleophile or a base. If it acts as a nucleophile, that phosphorus needs to connect to my reactant and it would show up in the product. Does it show up in the product? Yeah, which means what's that reagent acting as?
Nucleophile.
Acting as a nucleophile. Which means what does this green structure have to act as?
Electrophile.
Has to be an electrophile. That carbon needs to have some kind of positive character on it. Okay? It can't be formally positive because we're trying to draw neutral species for each of these reagents. So what could I connect to it that would make it partially positive? A good leaving group. Okay? And at this point, I could put in any good leaving group. I could put in bromine. I could put in chlorine. Because I don't know the reagents at this point. But if I walk a step further back, the reagent that I add to get here was PBr3. What do you see in PBr3?
Good leaving bromine group.
I see a lot of bromines, which likely means that X is bromine. Which means PBr3 somehow reacted with something to make this green structure. And yes, this one is challenging. How do you decide what that previous structure should be? Okay. We can't fall back on the chemistry of these pieces. Okay? Because it doesn't always work to let's just look at the chemistry. Okay? Kumbaya, and it just makes sense. No, it doesn't work here. We would have to know that reagent, and that reagent specifically reacts with
OH chemistry.
alcohols to convert them into, actually you're better. Okay, OHs, it specifically reacts with OHs to convert them into our bromides. And now what do I have? I have all the answers that I can now draw into my boxes. Okay? So some of this question, okay, because the class, when I looked through at it, 2 people in the class have started this homework assignment. Okay? One happened to be here when we were talking about what question to look at. And they're like, yeah, I didn't recognize that chemical reaction, so I just didn't do it. Okay? I hadn't watched all the lectures yet. I perfectly get that. That's fine. Okay? Did we solve it? Have any of you watched any lecture on the Wittig reaction? And yet, if you use the content that I've been trying to get you, you get 2/3 of the question. And the remaining 1/3 of the question was content you've already been tested on. The conversion of the alcohol to the bromide, that was Unit 1. So all the unknown stuff that you're like, I don't know what this is stuff that you could reason through using the tools that you have already at your capability. Okay? Potentially more importantly, okay, nobody, as far as I could tell, did this on their own. I said, I want everybody up the boards and you guys work together to figure it out. Nobody just sat there and just figured it all out and did it all on their own. You had to rely on other people to help point out things. Okay? Even if there was someone that knew most of it, they still talked through it to the point where other people could get on board with what was going on within that content. To that end, when you do your homework, are you talking to other people? Or are you sitting at home by yourself, stumbling through it blindly? That's your choice. Okay? You can absolutely do that. But what I'm trying to get you to realize is that you have a whole hell of a lot of power in your colleagues that you can leverage to do a whole lot of really cool things. Not just getting through the content, but actually learning it and understanding it. And in that, start to ask questions of like, but that hydrogen's not acidic. Why is it not acidic? That hydrogen. Why is that hydrogen not acidic? Wow, it's moving around on my screen. Oh, it's moving there too. Okay. Why is that hydrogen not acidic? Hydrogen's not going to be stable. If if we go through and talk about acidity, we look at different things. We would look at the atom effects. Okay? What atom would hold the charge if that hydrogen was removed? Carbon. Well, carbon size is small. Carbon electronegativity is low. Okay? Those are things that would make us say, that's not acidic. We might even push to say, well, that's an alkane functional group, and alkane functional groups are not acidic. If it's not acidic, why could we do it? Okay, the negative carbon, so we've got a couple different ways that you could describe that, so I'm going to direct you. I'm going to say the negative carbon. What can you tell me about that negative carbon? That we literally just said about why the hydrogen was not acidic. Is this carbon going to be able to stabilize that negative charge? No. So why can the black hydrogen act as an acid? What am I throwing at it?
Base.
Do better than a base.
Stupid strong.
Yeah, you're looking at something that's rock level strength and not like the little boulder like the dude, right? Okay.
Yeah.
I needed to explain it for you.
Like throwing rocks at people.
Dwayne Johnson. Is that better?
Yeah.
Okay. That's a really, 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 really strong base. I can remove that hydrogen because I'm throwing a stupid strong base at it. That's why it can react. But there's more to it. Why else could it potentially react? Okay. The resonating word. We could look at the product and we could say, doesn't that product have resonance? Okay. That resonating word. So we could look at the product of that. Oh, resonance allows that to stabilize. Because if we think through our enolate chemistry, because everybody loves enolate chemistry, right? Okay. I can make a negative carbon. But I'm not throwing a stupid strong base at it. I can throw hydroxide at that, and I get a decent amount of that negative carbon. Why? Resonance. The resonance of that product allows, as I not show it, the resonance of that product helps to explain that it's actually a lot more stable than we were initially thinking. Okay? So the resonance of this phosphorus structure helps to explain why we could remove that hydrogen. So let's take a look at that resonance structure. Are you all actually happy with that resonance structure? Some people are saying yeah. Mahassan's saying no, she doesn't. Anybody else want to say no? She says no to everything? Is that what you said?
No, you noticed everything.
Okay, why are you saying no? What do you mean the phosphorus only has one lone pair? I see no lone pairs on that phosphorus. And if we take a step further back, does the phosphorus there have any lone pairs? No. Say again? The carbon, no, the phosphorus is a good place to go. There's 5 bonds to that phosphorus. We have exceeded the octet on phosphorus. Are we allowed to exceed the octet on phosphorus? Yeah, we are. Does that upset anybody?
No, because it's
All of OChem 1, what did we say? Octet, 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 don't exceed the octet, never exceed the octet, never. But
it's in row 3.
why in OChem 1 did we never exceed the octet? And even then, that wasn't true. We did exceed it.
Because we were working those first 2 rows of that.
Almost all of OChem is in those first 2 rows. And in those first 2 rows, we can't exceed the octet. When we move into the 3rd row, guess what happens? We can exceed the octet. Why?
More orbitals.
That 3rd row gives us access to the d orbitals. Those d orbitals are what's allowing for the expanded octet. Phosphorus being in that 3rd row has access to the d orbitals, can promote up, and that's what's allowing for the expanded octet. Again, we didn't do that in OChem 1 at all, right? Not at all, like, I don't know, with sulfuric acid. Yeah, we expanded the octet there quite significantly. Okay. When did we expand the octet? Because there's a reason we expand the octet. That's a much harder question. It generally pushes back to Gen Chem. Minimize charge. Why are we looking at the phosphorus with the double bond? Because if we do that resonance, what happens to the formal charge? When we look at sulfuric acid, why do we do the octet or expand the octet? Because if you actually draw out the Lewis structure following proper rules, what you get, oh God, I can't believe I did this. Bear with me, I'm coming. There it is. Ta-da! That's what you get. That's a crap ton of charge. I don't like charge, so what do? I move a pair of electrons from the oxygen down to make a double bond. That gets rid of the negative charge on the oxygen, one of the positive charges. I move another pair down. So we're expanding octet to satisfy charge, or to minimize charge, if and only if we're using a third row element, or lower, technically. Kind of makes sense? So are we ready for the next level question? Because you're now getting a little bit of electron-Wittig reaction. Why did SmartWork not show that really happy, stable structure is the final answer? Why did they not show this? Why did they instead show, call it a red box, that? What's that?
It's more useful than best.
So cool. I like that idea. Yeah, we talk about useful and best. Except when we talk about drawing all our Lewis structures, what did we say is our rule? You always draw the best. We actually only bring in the useful for our knowledge to predict how it chemically reacts. And that useful structure is useful for that. And you could argue, interesting, that that black box is best. There is an argument for that. General consensus is it is not the best structure. That is actually why the red one is drawn. So why is the black one not the best structure? Minimizes charge, shouldn't that be grand? Why don't we do that? The argument that's floated, if we look at the lone pair on that carbon, what orbital is it in? A little bit. sp3 verging into a p orbital. If we look at the phosphorus, what is the phosphorus contributing to that double bond? Or what is the phosphorus contributing to that carbocation, or not the carbocation, the positive charge? To make a pi bond, though, it has to be p orbital. So we're talking, well, you're talking about p and p. Why is that a problem? Because we're actually missing a little bit of information. Be more specific about the type of either sp3, it's probably easier to say p, for the carbon. What p orbital for the carbon are we bringing in? And as a hint, it is different than the p orbital that the phosphorus brings in.
Difference like an X, Y, and Z? Like,
Nope. Not a bad idea. What p orbital does carbon bring in? If we look at carbon's electron configuration, its electrons are located in the 2p orbital. It's the second energy level. So if I was to draw the 2p orbital, ta-da, there's the 2p orbital. If we now go through and look at the phosphorus p orbital is the 3p because it's an energy lower down or higher up, depending on how you want to look at it. How does the 3p orbital look?
Different than the 2p.
The question is, how does it look different? As a hint, it does not look like this. it looks more like this. It looks bigger. It's a higher energy level. It's bigger. Why does that matter? Now what are we talking about? The pi bond exists because of what? P orbital overlap. There's a whole hell of a lot of this 3p orbital that isn't overlapping. Which means that's not a particularly strong double bond. And if we're going to say it's not a particularly strong double bond, really what we're saying is we're more heavily emphasizing the negatively charged structure. And that's the differential between it. That's kind of neat. See? Atomic orbitals. You're friends. Okay? The other thing that we'll kind of add as an extra little piece, this structure is so special in its chemistry that we get a different name, right? Because anytime we get a fun new chemistry that's kind of bizarre and out there, we always name it. Sometimes we name it after the person, sometimes we just give it a different name. The name we give this is YLIDE, or a yllid. Okay? So you can hear reference to ylids. Okay? It does mean something specifically. I honestly don't remember. I'd have to Google it to figure out what the term meant. But okay, when we're talking about Wittig reactions, they do refer to ylids. Okay? All right, another question. Triphenylphosphine. What did the triphenylphosphine, PPH3, act as? Did you actually say nucleophile, or did you go file? Okay, there must be some fuzz in my ear. Okay, nucleophile. Okay. Does anybody have a problem with PPH3 acting as a nucleophile? Yeah? Why?
Well, clearly doesn't like being positive. Because it's positive, it doesn't.
So we could go through and say as a nucleophile it forms a positive charge, and we don't like phosphorus with a positive charge. Nitrogen did it all the time, though. If we go through and do our Hoffman eliminations, we put positive charges on our nitrogen. So in and of itself, if nitrogen's capable of getting a positive charge, phosphorus should be even better. Why? Why should phosphorus be better than nitrogen at holding a positive charge?
Bigger.
Size. Okay. Why else might we question the nucleophile characteristic?
Big.
Okay, it's big. And what are you talking about when you're saying it's big?
It's hard to
Is it the phosphorus being big that you're complaining about?
feel.
Yeah, that's what I would argue. Okay. I hate the pronunciation game on that equally. So when we draw it out, you'll always see us just draw it out as the pH so that we don't have to go through all the detail. But remember, those represent six-membered rings. Those six-membered rings are all quite large. And if they're going to be quite large, what is that going to do to the accessibility of that pair of electrons?
Reduce it.
It's going to reduce it. So we might predict that that's going to be very challenging to act as a nucleophile. Okay? I don't have a perfect answer for this. In fact, I don't have really any answer. This is the first time somebody actually asked it enough that I've been forced to come up with a question or an answer for it. Okay? Those phenyl groups are very, very large, but I can see two things potentially contributing. One is a half-assed answer, and the other one's half-decent. What did we say was special about phosphorus?
Big.
It's big. And if it's big, there's more surface area around it so that we could put those phenyl groups, even as large groups, enough dispersed around it that we still get access to that lone pair. Okay? Literally just spitballing, just making stuff up. Okay? The potentially more appropriate answer that is very half-assed is, we know it works. This happens. So whether we like it or not, it happened. We know it works. Okay? Well, you could make the argument that I don't think it should work, which is fair. But since it worked and someone proved it worked, what do they get to do? They get to name it. Oh, you mean like we call this the Wittig reagent? Yeah, there we go. That could be the reason why it gets named. Is it's navigating through several pieces of chemistry that we would say, no, it shouldn't do that. And yet it does. Kind of makes sense? Questions about it? No? Okay. Recording. So, conveniently does fit kind of the same pattern because we're talking about weird elements like phosphorus and nitrogen here. So we could go through and look at this and try and run the same argument that we've run with everything else, is where do we see chemistry? Which was not a rhetorical question, that was actually an actual question.
On the nitrogen carbon, pi bond.
Okay, I like the addition of words there. So on the nitrogen carbon, okay, and extra emphasis on the pi bond, as in that structure or that formula is hiding a whole hell of a lot of chemistry, okay, that we need to be aware of pretty much instantly. So that if we're going to draw out this structure a little bit better, hydrogen, if I could go that dash to that carbon, and then let's expand it and show the bond to the nitrogen, what do I have a problem with here?
Corresponded on the
I'm missing a whole hell of a lot of octets. And that's because that's a triple bond. Okay? And if we're going to emphasize, I'm going to emphasize those, well, we'll just emphasize one of those lines. What is special about one of those blue lines? Technically two of them. How would we classify that pi bond?
polar pi bond.
This is a polar pi bond, which becomes particularly relevant because when we're talking about this particular unit, what are we looking at?
Polar pi bond.
Polar pi bonds, and in particular, the chemistry associated with polar pi bonds would be nucleophile additions. Okay. So cool, we've got that polar pi bond. If we wanted to draw a resonance, we could draw a resonance. I'm just going to do it for giggles. So we got a negative and a positive. Okay, and we've got that kind of system set up. Okay, cool. That sets up some chemistry. I'm kind of okay with that chemistry, mostly because LAH is a bit of a cop-out. What is LAH? What element is L? Lithium is not L. Lithium is Li. What element is L?
There's no L's on it.
There are no L's on the periodic table, which means what we're looking at with LAH is a shorthand for the name of the compound. Okay? I would argue, again, this is something that should be more defined. Okay? And we could go through and say that it is lithium. So those people saying lithium, I get it, but that, again, aluminum hydride, and that's where our name is coming from, where LAH is coming from. So if we were to draw that out, we've got our lithium, we have aluminum, and we have a hydride. We'd be missing a whole heck of a lot of octets, so this is where knowing how to convert that name into a formula would come in handy. And what we're looking at for our formula is a lithium ion cation and an aluminum anion. Okay, we could drop the lithium off as a spectator, which is fine, and we now have our lithium aluminum hydride. How does lithium aluminum hydride react? What is the reactive atom? I love the back out of that. That was awesome. Where's the negative held?
The aluminum.
On the aluminum. Is the aluminum the reactive atom?
No.
No. Why not?
Weird metal stuff.
So we can throw the weird metal stuff at it, because I throw that at it all the time. Okay? What is one of the characteristics of weird metals?
Oh, bromine. We've seen this with bromine, right? Where BH.
Bromine's a non-metal.
Well, it's
Boron.
It's.
You're talking about boron,
my
sorry.
bad.
Yeah. Go, because that's a good connection.
Boron does the positive. It becomes positive, and the hydrogen becomes negative because we do that.
So what you're remembering is our BH3. Our pi bond comes out, reacts with the boron as an electrophile, and it shuttles an H minus. Okay, that's not an R, by the way, that's a bond. In case anybody wanted to challenge me on that. Okay, with the hydride coming back. So that's a neat observation. Okay, and you might be not referencing that specific reaction, because if I look at that specific reaction, how is that different than the aluminum hydride?
We got a non-polar pi bond, and this time a polar pi bond, or
How many electrons are on the boron? How many electrons are on the boron? 6. How many electrons are on the aluminum? 8. Okay, so there's a differential there that doesn't quite fly. The boron can't act as, or the aluminum can't act as an electrophile. Okay, but the same kind of chemistry is going to come about. Okay, the hydrogen was negative in the BH3. Why was the hydrogen negative? There were a couple things. One, the boron having that empty p orbital helped, but there was another part for why that hydrogen was negative. What charge is the hydrogen in HCl? What charge is the hydrogen in water? Charge is the hydrogen in methane? Not. Okay. Why did it change?
The difference.
It's the difference in electronegativity. What's the difference in electronegativity between boron and hydrogen?
oh,
Hydrogen is actually
more electronegative.
more electronegative than boron. What's our electronegativity trend down a column? It decreases. So if hydrogen is more electronegative than boron, what is hydrogen in comparison to aluminum?
Even more.
Even more electronegative. Okay, so when we're seeing lithium aluminum hydride, the primary reactivity that you should be seeing in that particular reagent would be H minus. Okay, and H minus in a fairly particular chemistry, that's not high, that's H with a lone pair. Okay, typically acting as a nucleophile, it does have base characteristics. Okay, not acid characteristics. Why not acid? What are acids? Should be. They're H plus. This is H minus. So it could act as a base. That's one of the complications of this reagent. But this is our primary way of getting hydrogen nucleophiles is through lithium aluminum hydride. Okay? Why does this become valuable to us? Lithium aluminum hydride can give up a bunch of H minuses. Where could those H minuses go? To our positive. Okay? So if we set up our reaction, our nucleophile can come in, attack. I don't have to show the breaking of the pi bond in that particular structure because I already broke the pi bond. What do you think should happen to the stereochemistry here? Why should it stay the same? Did I do any chemistry at the carbon where the stereochemistry is? The stereochemistry is located specifically at that carbon. I guess we can color it same color. There. That carbon isn't chemically reacting, so we don't need to worry about it. Right? We look at the product of this reaction, what do you see? Should be a couple different things you see. Should we do hints? Hints are always fun. We'll go in order of importance. What do you see? A polar pi bond. Okay. What else do we see? We'll come back to that one. That's an important statement, but not yet. Okay? We should also see that we have a lone pair on our nitrogen. Okay? So when we go through and consider this one, the reactivity, we might say, well, I want to cancel that reactivity on the nitrogen first. Turns out we don't have to worry about that one as much because we're floating around in a solution of it's not in a solution of acid. We're in a solution of H minus. We're extremely negative right now, so that negative nitrogen is actually more stable than where we started. So we don't have to stress about that one. Why should we stress about the polar pi bond? Lithium aluminum hydride supplies H minus, a very active hydride nucleophile, which means it could react again. So what do I need to do? It's a good question, and it's always one that chokes me up and I screw it up. In this particular case, I've done this one enough that I'm fairly confident I'm doing it correctly. And since Mahasan completed it, she might be able to say that I'm on the right path. Yeah, cool. That makes me feel better. Thank you for that. Okay. And then I believe, Tyler, what you're noticing here is that that first lone pair made it a negative. Okay, if we're looking at that red one, and we now have a second lone pair making it another negative, we're looking at a doubly negative nitrogen. And yes, that is exceptionally reactive. We don't want to be forming that. But why can we do it? We're in that hydride solution. Okay. Take it a step further for why it can do it. One of the byproducts of this is you get that aluminum floating around, missing now a hydrogen. Okay. What could that aluminum with now that missing orbital do? It can coordinate to the nitrogen to stabilize it long enough for this system to react out. What's that?
Even though it's not charged.
You tell me. Does boron, even though it's not charged, react with a pi bond? Yeah. Okay. Before we get too excited about moving further, Andrew asked an interesting question here because he said he saw another pi bond. Is there another pi bond in this solution? Yes. We still have the alkene pi bond. How does the alkene pi bond react? This is now going back to our Unit 1 of this semester or Unit 4 of OChem 1. How do pi bonds react? Sorry, that particular kind of pi bond, a non-polar pi bond. It acts as a nucleophile. Hydride is also a nucleophile. What happens when those nucleophiles get near each other? Nothing. It's only because we have a polar pi bond that the hydride can go through and react. So that non-polar pi bond does diddly squat. Okay. That probably just dated me, but whatever. Okay, make sense? So we say, yay, we're done, and we answer that, and of course we're wrong because we didn't finish it. Because as was pointed out earlier, there is a second step. We would follow this up with H3O+. So H3O+ comes through and is going to supply us what?
Hydrogens.
Be more precise, positive hydrogens. So our positive hydrogens could then go through, I'm not going to draw out the mechanisms for those. But those positive hydrogens could come through, protonate our negative charges on our nitrogen, and we would now have a glorious neutral structure, and we could enter this glorious neutral structure into smart work and be happy and done. And of course we're wrong. Why are we wrong?
So we have one more lone pair.
That extra lone pair. We're like, but it's neutral. I shouldn't have to protonate it.
We're in an acidic environment.
In an acidic environment, nitrogen acts as a base, which means if I add H3O+ to this molecule, I lose that last lone pair, which then means the product that I get is the nitrogen with a positive. That should be where you ended it. Okay? This nitrogen chemistry will come back to haunt you, particularly for those people that have to move into biochemistry. Okay? It is also going to haunt you through this semester as well. We'll talk about some of the kind of precursor molecules or reactions that you would do in biochem, okay, to a very simple level. We'll talk about how it can scale up in difficulty when you move into biochemistry. But it centers on that acid-base chemistry of our nitrogen. So we've got to be real careful to address that. Okay? Organic chemistry, unfortunately, half the time we pay attention to it appropriately, the other half of the time we don't, and we'll draw it neutral as a neutral product. I really wish we were more consistent behind that application. We just aren't. Okay? So you can draw it out neutral to start within a homework assignment, and then be like, dang, I got it wrong. You probably got it wrong because you forgot to protonate. Okay? Protonate it, make it charged, and then you should be fine. Okay? So just be aware of that as an issue. Go ahead.
So in the acidic solution, nitrogen always acts as a base. So is there a reason, because carbon and nitrogen, they're not like different in electronegativity?
Carbon and nitrogen? No, they are.
Is it enough of a difference for the nitrogen to take its lone pair and like satisfy
To
it from
act as a leaving group?
Yeah.
No, not in and of itself. No. You would have to have something to force it off, and that was one of the discussions that we talked about when we looked at the amine chemistry.
And we would probably need something basic, and we don't have anything basic because we're in
Yeah.
it.
Make sense? We good with that one? Do you have any follow-up questions on that one?
Why did you do the pi bond orange right now?
I drew the non-polar pi bond orange because we addressed all of the polar pi bond
Okay.
chemistry, and Andrew had pointed out that we had another pi bond. Why did we not react that one? We don't react that one because it's not a polar pi bond. It
Okay.
has to be a polar pi bond to actually cause this reaction to happen. Okay, a couple attempts on this one as well, so we know there's some challenges behind it. Okay, and again, remember, not everybody sees the same thing. We're pretty much at time, so I'll go through this one kind of fast. What stuff do we see?
The NaH, the negative hydrogen.
NaH is Na plus and H minus, which sets us up with really just H minus. This H minus is very different than the, lithium aluminum hydride H minus. This H minus is solely a base. It has virtually no nucleophilic characteristics. Okay? So if it's going to act as a base, what does it do? It needs to find an acid. Okay? I don't care about step 2 yet, so I need to find an acidic hydrogen. And I would look at that structure, and how many hydrogens do I see?
5. I mean, that could be acidic.
Okay? I would argue we see no hydrogens. So what we would try to do is then visualize all of them. So if you're picking out all the hydrogens, counting them, okay? So you could see that there was 5 on the aromatic ring and then 5 on our ethyl group. Of all of those, we really only care about 2. We care about the 2
Right next to the.
at the alpha position on our carbonyl. Okay? So what happens? Our base comes in, deprotonates. This makes a negative carbon. Do we like negative carbons? No, we don't like negative carbons. You go, oh, but it's okay because the environment it's in. Negative carbon versus negative hydrogen, you're right, it is slightly more stable, but that's not going to be a great driver for that acid-base reaction. Okay, what's going to allow this reaction to happen? We have that resonance stabilization. That resonance stabilization is what explains the stability of our reaction, allowing it to occur. Between those two Lewis structures, which one is the useful one? first one is our useful. The purple one would be our best. Okay, so you don't have to draw the purple one. Okay, you could just stick with the black one, or what you can do is still navigate from that one to a product. Okay, your electrons are going to have to swing back down, which means we're building charge on this carbon. Okay, that carbon being negatively charged needs to find what? What does a negative charge need to react with? A positive. So what do you got to find? You got to find an electrophile. The NaH doesn't have any electrophiles, so we're kind of dead in the water, at least at this point in the semester. Okay, so we look to step 2, and in step 2, we'd have to be looking really carefully. We have an I at the end of that, and what is I? Iodine, which is
Leaving group.
a great leaving group, and if it left, what would we have?
A positive CH.
We'd have a positive carbon, which would be a great electrophile. Whoops. Should not have turned that. Carbonyl there. These are reactions that it's real easy to lose where your bonds are. So here's our new bond. CH2, CH3. Kind of makes sense? Right. This is leveraging that enolate chemistry. That's what's allowing it to kind of initiate. Right? But once we have that enolate, we have a nucleophile, we can now do standard substitution reactions. Okay. I have to be done, but go ahead and ask the question.
I understand that we're supposed to use the most useful one, but why wouldn't it react with the best?
So there's an interesting question between useful and best. Why does it not react with the best? It does. Remember, which of these two structures exists? Both. When?
Same time.
Simultaneously. So there is, at no point is there structure useful, structure best. You've got a hybrid unicorn of a horse standing next to a rhinoceros, and the shadow looks like a unicorn. Right? Well, that doesn't work because you have a horse and a Can I delete? Ignore that. These are mixed. Okay? You're looking at that kind of action of the arm constantly moving kind of system between these two. Okay? Between these two, which one is more likely to produce products? Right? Is the oxygen more willing to share the electrons, or is the carbon?
The carbon.
That's where my reactivity is going to be. Okay? Could the oxygen act as a nucleophile? Yes. Very limited circumstances, very controlled reactions, but there are reactions where you can force that oxygen to act as a nucleophile. But it's limited. With that, I'm